Hello everyone, in this video I want to look at a weak acid strong base titration. So we're titrating a weak acid with a strong base, and specifically we're looking at the titration of hypobromous acid, which has the formula HOBr with NaOH, which is of course a strong base. Alright, so thinking of a little picture that we might want to draw, we have a conical flask, and that contains our hypobromous acid, and in our burette we have our sodium hydroxide. Alright, so in other words, we start with a certain amount of hypobromous acid, a concentration and a volume. So in other words, we know the number of mole of that acid, and we slowly add sodium hydroxide to that. Alright, of course this leads to an acid-base reaction, alright, which is as follows. So hypobromous acid, HOBr, aqueous, reacts with sodium hydroxide. So now sodium hydroxide is a strong base, so it fully dissociates in water or an aqueous solution, and therefore the active species would be OH minus. Correct. All right, and this will deprotonate the acid, so it will form water and of course the conjugate base of hypobromous acid. Let's give myself some more space here. I know why I always move for some reason to the side. So OBr minus aqueous. Alright, so that's our initial analysis, and it's a strong acid reacting with a base, so it should be a largely product forming reaction, but hopefully you immediately recognize that this conjugate base would be able to hydrolyze with the water. So therefore there is a reverse reaction that can also take place the moment that that base forms. So technically we are looking at an equilibrium. HOBr aqueous, that reacts with, or the OH minus is added, that can then form the water. Water aqueous, water liquid, goodness sake, water liquid, let's just write that properly, will form water liquid, and of course OBr minus aqueous. But OBr minus aqueous is of course in its own right, it's a conjugate base, but it's also a base. In other words, it can react with water to reform our acid and hydroxide again. Alright, so in other words, we must think of this as an equilibrium system as we go along. Alright. Yes, alright, and there's something very important about that, because that means when this titration reaches equivalence point, we must actually think of this equilibrium as switching over. It will reach the point where our this anion will then dictate what the pH is, because it will be the only species left to dictate the pH. Alright, so you must make a big note for yourself that at equivalence point we expect the following. Right, at equivalence point we expect this equilibrium to, the words are not really correct to swap around, but in principle we expect then the reverse reaction, this reverse reaction, to be the dominating force, right? Because at equilibrium, these two reactants will be fully used up. So in other words, we're only left with the products. And therefore, this reverse reaction will be the only reaction that can take place. So in other words, the equilibrium that we are left with at equivalence point is OBr minus, so it makes sense to think of it then as a product forming equilibrium like this. words, we kind of swap it around, because then it becomes the dominating equilibrium. At the start, there's more HOBr minus as we add hydroxide. Once we reach equivalence point, the OBr minus becomes the dominating species, and so we flip the equilibrium around, and it starts forming HOBr aqueous and OH minus aqueous. All right, think about what the form is of this titration curve that we eventually want to plot. So thinking in terms of how the pH varies with the amount of sodium hydroxide added, we start with an acid, right? So we have an acid in the flask. So that means we should expect a low pH, a weak acid, but we'll have a low pH, right? And as we add sodium hydroxide, the pH should increase, right? So it should have an increase in pH. Eventually we'll reach an equivalence point, and then we will have a plateau at some stage. All right, so I mean the specific form now doesn't matter. We're just thinking about what we are going to do. And as we discussed, at equivalence point, our equilibrium swaps around, or we can think of it as the equilibrium swaps around, because the dominant species, or the only species present, is the conjugate base forming hydroxide. So that means we have hydroxide present at the equivalence point, then making the equivalence point basic. All right, so we expect an equivalence point with a pH of larger than 7. All right, and of course after the equivalence point, we expect to see excess OH, right? Because we keep on adding sodium hydroxide, we expect excess OH. We start with the acid, so that should dictate the pH over here. And as we start adding NaOH, we must of course think of this equilibria that we have here. And because we have this equilibria that we have here at the start, we know we have the acid and its conjugate base in some relative amounts present during this part of the titration. So that means the pH in this region, around about that region, is of course controlled by the buffer solution. All right, and that's a very important observation. So it means we have our 4 important points and 2 important regions, let's put it like that, because we have the initial concentration, or the initial situation, where we have the HOBr that will dictate the pH. We have our buffer region then that we enter, and then once we have ended the buffer region, we reach the equivalence point, and the equivalence point pH will be dictated by the amount of conjugate base that can form from the reaction, or from the the amounts of acid and base. And then once we've passed the equivalence point, the pH will be dictated by the excess amount of OH that we've added. All right, so those are the important things that we need to be on the lookout for. All right, so let's read each of these sections and see if we can identify what we are after. All right, firstly, just also ensure that your D says 35.5 milliliter, and then we can start looking at each of these volumes that we're adding. So now we're going to start adding NaOH and calculating the pH at different volumes. So our first pH that we have to calculate is when we are just interested in the pH of the flask when no sodium hydroxide has been added. So of course when we only have the weak acid present. And when we only have the weak acid present, of course we're only interested in, well, we have an acid with a certain concentration in water, right? So we're interested in this equilibrium that acid forms with water, right? So this acid has initial concentration, it forms an equilibrium with water, so protonating the water. It does not fully ionize because it's a weak acid, right? And its ionization will be dictated by its Ka value. And so we can summarize our information in a mass balance table, an ICE table, all right? And so you set that up, you calculate, you can make an approximation because you see its Ka value is very small as given in the question. It's much less than its initial concentration, which is given as 150 molar. And so you get the concentration of H3O plus. And once you have the concentration of H3O plus, right, then we can calculate the pH, because the pH is just equal to negative the log of that H3O plus. All right, and that's the basic idea. So you have an acid in just dissolved in water. It's a weak acid. And how do you determine the concentration of a weak acid, of the pH of a weak acid? Right, it's like we've always done. You need to determine what the concentration of H3O plus is at equilibrium. So it's a very standard question, this, in terms of you just need to know what is actually being asked of you. So that's the pH here, is the concentration of the acid technically, or the concentration of H3O plus, dictated by its Ka value. All right. Once we start adding NaOH, then of course we need to start thinking of it as a stoichiometry problem, because once we start adding NaOH, of course the OH minus reacts with the acid and it forms the OBr minus. All right, and we start moving into or onto the curve. All right, so it means it decreases the amount of OBr plus and it increases the amount of OBr minus present. All right, and then of course it means we need to start taking other things into consideration. Okay, but we must also determine where on the curve we are when we add these different volumes. So let's go ahead and look at B. So B says the pH of the solution in the flask after 10 milliliter of sodium hydroxide has been added. So when you read something like that, think it's a stoichiometry problem. So what we must do is we must determine how many moles of the HOBr we have in the flask. That's 7.5. And now we must ask the question, how much of the NaOH have we added? And we see that is 1 mole. So because it's a one-to-one reaction, right? So as always, you can think of it as just a reaction forming some products for this initial step, or you can think of the equilibrium, that's fine. It's a one-to-one reaction. So that means that our OH is limiting, right? Because it's the far less number of moles than the HOBr. So it means if the NaOH is limiting, it means there's an excess amount of HOBr. And that will be the initial amount minus the amount of NaOH that we've added. All right, and because the NaOH is being fully consumed, it means in principle at this moment it's consumed. This is an excess. All right, and we need to determine what its concentration is because it's in excess at the moment. So to get its concentration, we've added 10 milliliter of sodium hydroxide. So it's the 50 milliliter of the HOBr that we started with plus the 10 milliliter. So it's the number of moles of the HOBr left divided by the total volume gives us its current concentration. But during the reaction of this, adding this to this, our conjugate base is also formed. So in other words, it means there is a certain amount of it that is also now present during what that is now present because of the addition of the NaOH. All right, and it's of course dictated, its amount that's formed is dictated by the limiting reagent, right? It's dictated as always. It's always dictated by the limiting reactant. So the number of mole of OBr minus that's formed will be equal to the number of mole of the NaOH added. And you can calculate its concentration using the same idea. It's going to be in the 60 milliliter. So you calculate its number of mole, or its number of mole is the same as the number of mole of the NaOH added, the limiting reactant, and you can get its concentration. Now, in principle, you can argue and say, well, we should be therefore here, right? The OH minus is the limiting reactant, so we're not here in the titration curve. We are in the point of the titration curve where we have the acid in presence with its conjugate base. So therefore, we're in a situation where we have a buffer solution. All right, but I'm going to just show you the way that you can in principle do that. So you can use the Henderson-Hasselbalch equation to calculate the pH. And I want you to show you two different ways in doing it. So the first way is, of course, you can use your mass balance table. All right, and using this kind of mass balance table in the way that you have your HOBr and you have your OBr minus just with initial concentrations. So you treat it as if you have a common ion. And let's see if we can get the pH from that. Right, so you have your HOBr minus concentration and you have your OBr minus concentration that we've just calculated. And then you go ahead, you use your Ka to get the concentration of H3O plus to see how this equilibrium affects it, and you eventually get your pH from the H3O plus. Could we have used Henderson-Hasselbalch? Yes, we could have, because we're in the buffer region. You have your conjugate base in equilibrium with your acid, all right? And therefore, these conjugate pairs are in existence with each other. And because the approximation was valid, you could have used the Henderson-Hasselbalch equation. All right, so yes, you could have used the Henderson-Hasselbalch equation. In fact, use the Henderson-Hasselbalch equation and see whether or not you get the same pH when you look at this calculation. But this was to show you that if you forget for some reason that the Henderson-Hasselbalch equation is appropriate here, you can still use your mass balance table. All right. The only important part is that you must remember what type of equilibrium you are looking at here. So notice it's not this equilibrium that you are looking at here. You are looking at this equilibrium here because you want to use the Ka of the acid to calculate the hydronium ion concentration. All right, that's the only important part. You must always just remember what equilibria you're actually looking at. All right, but now that we've established, because you see we are indeed in the buffer region, let's look at the next volume that we should use. So what about if we've added 20 milliliters of sodium hydroxide in total? All right, so how many moles of sodium hydroxide is that? So that corresponds to 2 mole of sodium hydroxide. So it's still limiting in comparison to the total number of acid. So again, you go through it, sodium hydroxide is limiting. That means there's an excess amount of acid. We've now added 20 moles, so that means our total solution volume is 70 moles. So therefore, the concentration of our acid has decreased a bit, but in adding the sodium hydroxide, it means we form the conjugate base. If we form the conjugate base, how much of it is formed? It's dictated by the limiting reagent. All right, so the amount of the conjugate base formed is equal to the amount of base added, and therefore we have 2 mole of the conjugate base. The concentration is equal to the number of mole divided by the volume. There we have our 2 concentrations. We indeed know that as long as this OH minus is the limiting reactant, or it is indeed, much less here, it's definitely limiting, we are in the buffer region. So let's go ahead and use the Henderson-Hasselbalch equation. Right, and the Henderson-Hasselbalch equation is pH is equal to pKa plus log conjugate base divided by acid. And our conjugate base is OBr minus, HOBr is our acid. So we must use the Ka of HOBr as given in the question. And I get a pH of 8.20 for this, for these 2 concentrations. All right. And that's it. So now we're in the buffer region, and we've definitely established that. All right, so that's for 20 milliliters in total. So let's see how we can continue on. So the next amount of that we need to look at is when we've added 35.5 milliliter of sodium hydroxide. So still stoichiometry problem. How many moles of sodium hydroxide does this correspond to? So sodium hydroxide added is 3.75 mole and still less than the 7.5 mole. So it means sodium hydroxide is still the limiting reagent when it's 35.5 milliliter. But now this is a very interesting number of moles, an interesting volume, because this is exactly half of the number of mole of the acid. So it means that if you do the calculations, right, what will you get? So the amount of acid in excess is 3.75, and it means the number of mole of the conjugate base formed are equal. So if the number of mole of acid in excess and the number of mole of conjugate base are equal, I hope you recall that that is a very specific point in the titration. It means that we are halfway to the equivalence point, because the equivalence point is where this number of mole added would be equal, and hence both of these two species would be fully consumed, and therefore these numbers should be equal. But if we're halfway, so meaning the half amount of this has been added, we are halfway to the equivalence point. And that halfway point has the effect that means that these two numbers, so the number of mole of our acid and the conjugate base formed, are equal. And because we are in the buffer region, that's going to have an effect as follows. So look at what happens to your concentrations. Your concentrations are also equal, right? So 50 milliliter, the total solution volume is now 50 milliliter plus 37. So that means we have a total solution volume of 87.5 milliliter. So what happens to your Henderson-Hasselbalch equation? Well, pKa plus log concentration, that means it's pKa plus log of the same concentrations. That means you have pKa of log 1. And that means it's just the pH is equal to the pKa. And I mean, you can plug in that value and you get that. So therefore, if we are halfway to the equivalence point, or half, so in other words, half to the equivalence point, so specifically at the halfway point, the pH is equal to the pKa. Now you can physically see that. That is why the pH is equal to the pKa, because the amount of acid still left is equal to the amount of conjugate base formed. All right, because that is the effect of adding half of the amount of base needed to get to the equivalence point. Okay, so yes, you can remember just that the pH is equal to pKa at the halfway point, but this is now the physical reason why. You can physically see how the numbers cancel to get to this point. All right, so we're making good progress. And the next volume that we are interested in is once we've added 75 milliliter of sodium hydroxide, and after that then 90 milliliter in total. So it's still a stoichiometry problem, right? So what happens once we've added 75 milliliter of sodium hydroxide? Well, that means we've added 7.5 times 10 to the negative 3 mole. And that means we've reached the point where the number of mole of sodium hydroxide equals the number of mole of the acid. And therefore, we've reached the equivalence point, right? Because the number of mole of acid equals the number of mole of base added. So that means there is no mole of the acid left, right? So if you do the calculation, it means our initial number of mole of acid minus the amount reacted is 0. So it means its concentration, well, at least initially, is 0. Right, but our conjugate base is formed, and it is dictated by the limiting reactant, but there isn't a limiting reactant at the moment here because both of these are the same amount. So it means it's just equal to how much ever one you want. So it's equal to both of those. So it's equal to 7.5 times 10 to the negative 3. The question, however, is in what volume? It's when we've added 75 mole of sodium hydroxide, so plus the 50 mole initially in the acid. So that gives us 125 mole, and that means its concentration is now that. Now the question is, however, what dictates the pH? And remember, at equivalence point, it means both of these two species at the top here, our reactants, as looking at this equilibrium in this direction, has now been consumed. And we're only left with the so-called products of this. So in principle, it's better to look at this equilibrium now as switching around, because our reactants actually now become these products, right? It's OBr minus and H2O. So therefore, our question is, how does OBr minus react with water? And it forms HOBr aqueous and hydroxide. And the question is, what is the pH of a 0.0600 molar solution of OBr minus? And how would you do that? How would you calculate that? Well, you would use a mass balance table, right? Because it's essentially asking what is the pH of a 0.06 molar solution of a base. And you would do that typically by saying, I need to know what the concentration is of OH minus. That would give me the POH, and I would get the pH then from that POH. I have an initial concentration, and I'm just then interested in getting that concentration of OH minus at equilibrium. What do I need, however? I need the Kb of this conjugate base. But luckily, how do we know that Ka and Kb's of conjugate acid-base pairs link together? We know that if we have the Ka of the acid, we can calculate the Kb of its conjugate base using Kw, right? Because Kw times equals to Ka times Kb. All right, so you can calculate Kb of this conjugate base. And then it's the same old, calculating the concentration of OH minus through this whole procedure to get the pH. All right, so that's what happens at equivalence point. This equilibrium, I like to think of it as switches around. The only reason is because, yes, it's in principle just the reverse of this. So you can use this equilibrium as written and put the concentration here and say the equilibrium, look at the equilibrium as the reverse reaction is favored and do the calculation from there. But it's much easier to just look at it like this because it's OBr minus forming HOBr and OH minus. So yeah, that is what happens eventually. All right, good. So that is what we have here as at the equivalence point. All right, so that's 75 moles. Our F question said, what happens if we add 90 moles? Right, it's still a stoichiometry problem in terms of we need to check now what is in excess, and hopefully you see 90 moles corresponds to a volume of 9 times 10 to the minus 3 moles sodium hydroxide, and we only had 7.5 mole of the acid. So therefore the sodium hydroxide is now in excess, and that means the excess OH minus is what is going to dictate that pH. All right, so yes, your OBr minus can still hydrolyze, it can still contribute some OH minus concentration, but because it's a weak base, right, look at that concentration. It only contributes 5.1 times 10 to the negative 4 molar concentration to the OH minus concentration. What do you think is going to dictate or contribute more to the OH minus concentration? The 1.5 mole sodium hydroxide that you add in excess, so meaning it's the excess amount of sodium hydroxide that you add here is 0.01 molar, or the 5.1 times 10 to the negative 4 molar that this equilibrium can contribute. And the answer is, of course, no, it's the amount of excess that comes from the sodium hydroxide, right? So you can approximate it by just looking at the amount of sodium hydroxide in excess. So therefore, you only need to worry about how much sodium hydroxide is in excess, and it is 1.5 mole because it's the amount in excess minus the amount that reacts with the acid. That gives me 1.5 mole of sodium hydroxide. I need to divide that by the total volume to get the concentration of the hydroxide. So I've now added 90 moles. There's a 50 milliliter in the flask, or of the acid in the flask, and that gives me the OH concentration. And of course, from that I can get the POH, and from that I can get the pH. And you can see that's quite basic. All right, so there we have all the points that we're interested in. So now we can plot our titration curve. So what does our titration curve look like? Here we go. Well, we started at our low pH, which was just our acid in the flask. We then moved into our buffer region where we encountered our halfway point, where we saw the pH was the pKa. The buffer region, the pH was dictated by the Henderson-Hasselbalch equation, right? We had an equivalence point where the amount of acid equaled the amount of NaOH added, and we saw that that pH was indeed larger than 7 because of the hydrolysis of that conjugate base, which led to a pH larger than 7. And then once we passed that equivalence point, the pH was then determined by the excess amount of sodium hydroxide. All right, so, and that is in essence what happens when you add a strong base to a weak acid, and that is how its titration curve will look all the way through. And I mean, I've added a couple of extra points so you can do all the calculations in between if you really want to and check yourself. And that's how you don't need to remember it. The important things: where you start, going to the buffer region, what happens at equivalence, and what happens after equivalence, and what in each of those regions dictates the pH. What are the things that is important to look at and how they dictate the pH? That's actually what's important, because once you're in the region, it's kind of easy to calculate the pH. It's just more important to remember what is the thing that is actually causing the pH to be what it is in that region. All right. Thank you for watching, and I'll see you in the next video.